Let's go ahead and talk about machines for a little bit. And what I'm going to do is I'm just going to introduce the ideas behind what a machine is, and then we're going to go ahead and talk about four machines. Three of them are relatively simple, but one of them is a little bit more complicated, and I'll try to spend a little bit more time on that. So the basic idea of machines is not to give you free lunch. There's no such thing as a free lunch in physics. The thing you need to know is that for a machine, no matter what machine you use or whatever device you use or whatever you do for that matter, work cannot be created nor destroyed, just like energy cannot be created nor destroyed. So the input work that you put into a machine has to equal the output work that comes out of the machine. And even more so, perhaps the input work would have to be more than the output work. The basic principle is that you can't have more output work than input, but sometimes you can have less output work than input. And that's just because of inefficiencies of the machine, maybe some thermal uh, energy is created. So that's all inefficiencies that could come about to where you have to give more than you get back. But let's just go ahead and assume we have perfect machines which can output the same work as you put in. So if you remember the equation for work, it is force times the distance. And just on a side note, force and distance have to go the same direction for this to work out. So you have to have an input force and it has to be applied over a certain amount of input distance. And then what's going to happen is that machine's going to take that and jumble it up and do its magical thing. And then it's going to output a force and a distance. Now, the thing is, a machine is almost exclusively useful because we humans are weak. Yet we can do things for a long time. So generally speaking, when we use a machine, we put in a little bit of force over a long distance, and the machine takes that and gives us a large force over a small distance. Well, anyways, let's go ahead and look at a few machines here, starting with the lever. So here's the equation for the lever. F out divided by F in is equal to L in divided by L out. Let's talk about what that means. Let's say I have a fulcrum and I have a very, very sturdy and light plank, maybe made out of some titanium or some carbon. And what's going to happen is that I want to pick up that green box on the left. What do I have to do? I could just pick it up. But if I want a machine for that, which is this orange and blue lever, I can also push down on the right side to pick up the box on the left. Now, if the lever arms are the same, that is the distance between the blue fulcrum to the red arrow or the red input arrow. If that length is the same as the blue fulcrum box to the left red arrow, then you're going to see that there's not going to be any advantage. I'm going to have to push down with an F amount of force, and I will get an F amount of force back to to lift the green box up. However, the only advantage would come about if the distance between the blue fulcrum to the output red arrow was shorter than the blue fulcrum to the right red input arrow. And if that's the case, the longer lever arm, as stated in this picture, would obviously be longer than the shorter lever arm. And thus you would have to push with less force, but over a longer distance because it's a longer lever arm. It's gonna be lifted up a lot higher. You're gonna have to push it over a longer distance down in order to lift up the heavier green box a shorter distance up. So how does that look in the equation? F out is going to be larger than F in, and that's what we're trying to do. And that's only achievable if the lever in is greater than the lever out by the same ratio. So if I make my right lever, that's the lever, my input lever, if that's twice as long as my output lever, then I need half the force to lift up the box. That is basically the essence of a lever. The next is a pulley. And a pulley has no real equation, but it's just words. The number of pulleys in the system determines how many times output force is divided from the input force. So, for example, if I want a simple pulley of 1 and I want to lift up a 100 Newton, looks like some sort of dumbbell or some sort of anchor or whatever, I need to supply 100 newtons of force to do that. Now let's go ahead and make a two pulley system where I have one pulley hooked up to the ceiling. I have a hook that's hooking onto the ceiling as well. And I have another pulley that's being wrapped by the rope connected to the hook and wrapping around the first pulley. If that's the case, kind of that contraption as you see for the number 2 picture, I can lift up 100 Newton uh, bar of metal by using only 50 newtons of force. Well, that's great. So I have 2 pulleys in the system, and that divided my input force by half. So what does that mean though? As I said, work is not created or destroyed. I did not get a free lunch. So I can lift up a 100 Newton bar with 50 newtons of force, but guess what I had to give for that? The 100 Newton bar is only going to be lifted up 10 centimeters, whereas I have to pull 20 centimeters in order to achieve that. Let's look at the third one right here. You got 3 pulleys, and I'm not going to explain how they're set up because you could clearly see it on the picture here. But let's just say now I have to lift that same 100 Newton bar. I'm going to actually need only 33.3 newtons, so 1/3 of that worth of newtons of force in order to lift it up. And yet again, there's no free lunch. Even though I have 1/3 the force to lift it up, I need to pull on this rope 3 times as far. So I have to pull on the rope 30 centimeters to lift up the bar 10 centimeters. For pulleys, same thing. You got 100 newtons. I only put in 25 newtons. That's a fourth of it, but I have to pull 4 times as far. Now, a bicycle is a little bit different in 2 ways. One, this is a little bit of a tougher concept that we're going to have to learn. But the first thing I'll talk about actually is the other one, which a bicycle does the exact opposite of what most machines do. Now, remember I said that humans are weak, so we want to apply less force over a longer distance so that we can get more force over a shorter distance, such as low jacking a car. Now, a bicycle is the opposite. We apply a lot of force over a short distance so that the bicycle can, with low force, can go a further distance. Obviously, you kind of know that. It's whatever force you put on the bike pedals. You know that the bike will go further than what you would have gone if you were to just walk. So the bicycle is one of those backwards kind of machines, but it's still a machine nonetheless. Now, this equation that you see in the yellow banner is a little bit complicated. Let me explain each variable to you. F out is the output force that is produced from the wheels of the bike that's pulling you forward. So if I were to, let's just say I was on a bike and I was stopped, I push on the pedals and the bike is going with a force of F out, but somebody is holding me, so I can't go forward. Now, if that somebody had one of those force sensors that can detect the amount of force that you feel, that person would see F out as I'm pedaling to try and ride the bike. And we can probably predict that F out would be substantially less than F in. So F in is the amount of force that I push on the bike pedals. If somebody were to instead have another force sensor and they force sense my foot, they would see that I am pushing harder on the pedals than the bike is going. Now, this is kind of one of the reasons why you can't go up a large hill or any hill really with a bike on a high gear. That is because the force output is so small compared to your force input. But that's a little bit different, a little bit more complicated than we need to go into right now. So force out is the force from the bike. Force in is the force on the pedal from you. R in, so R sub in is the radius that you're going to, that the bike pedal is. So bike pedal, as you see that little silver piece right there, I'll put my laser pointer on there. You see the bike pedal right here. So that radius is from here to here, okay? That's R in. R out is the wheel, which is from here to here. Actually, it's going to be the wheel that's connected to the bike pedal. So it's actually going to be the back wheel from here to there, okay? And so, but it doesn't stop there. And the reason why is because you also have gears. So if it was only that simple, that would have been great. But we have this thing called gear ratio, which basically goes as N in versus N out. Basically, what the gear ratio says is that if you have, say, this ratio of N in divided by N out, and let's say the gear ratio was something like 3.6 to 1, that is the gear ratio of a Toyota Tacoma TRD off-road, all four-wheel drive, double cab, long bed. That means that the engine will rotate 3.6 times for every one time the wheel rotates, if you will. So the same for a bike. If I have a gear ratio of something ridiculous like that 3.6 for N in versus the 1.0 for N out, that means I'll have to pedal 3 times for every one time this wheel rotates or revolves. Now that doesn't make any sense because obviously bikes tend to do the opposite of that. So a more realistic gear ratio for a bike would be something like N in being 1, N out being like 3 or something like that. Okay. So you can go ahead and plug in, if you know all these things like the gear ratios, you know the R in, R out, and you know one of the F's, you can simply solve the other F. So that's what this equation talks about. It talks about the gear ratios, the ratios of the radii for the engine, which is the bike pedals and the wheels, and then the ratio of the forces. That's the force of you versus the force of the bike output. Okay, so that's a little bit more complicated, but nonetheless, it's still an equation where you need to know all the parameters except one in order to find the last parameter. And the last one is the hydraulic lift. So the hydraulic lift looks a little funky as an equation, but basically it's 2 equations, or 3 if you will. Basically the equation says, well, first let's talk about the picture. You have water, which is incompressible, and you have it trapped within 2 pistons. First piston has an area A1, second piston has an area A2. Now, generally speaking, you want A2 to be larger than A1. And the reason why is because that means you could push with less force over a greater distance in order to lift something like a car up the other piston. So what we're saying here is that the output force divided by the input force is equal to the ratio of the output area, so the area of the piston which is pushing up, divided by the input area, which is the area of the piston that you yourself is pushing down. Okay, so that's the first equation right there. That ratio of forces is equal to the ratio of areas. So if I want to lift up a car that's like 1,000 newtons, it's a small car, it's 1,000 newtons, but I can only push 100 newtons. Obviously, I need a ratio of areas for the piston to be 10. So I need the output piston to be 10 times more than the input piston, because I can only push 100 newtons, but I need to lift up 1,000 newtons. So there's that. Secondly, just with the conservation of energy, if I push down with an F in force, I need to push a lot further than the piston that's outputting the force. So therefore, if I want to lift up a 1,000 Newton car 1 meter, I need to push my my input piston 10 meters in order to do that. Okay, so that's what the hydraulic lift equation says. So it's basically, you can say F out over Fn is A out over An. You can say F out over Fn is Dn over D out. Or you could even say, less useful in a way, is A out over An is Dn over D out. So basically you have three equations, two of which are more useful than the third. And so that's basically all you have there. You have basic purpose of machines, four types of machines: levers, pulleys, the bicycle, and the hydraulic lift.